Welcome to Talk Tensors.
Glad to be here.
So, imagine you have a brilliant employee.
Okay.
Like, this person is an absolute genius. They can write a flawless legal brief in, 10 seconds.
Right. Highly capable.
Exactly. They can synthesize a 100-page financial report in a minute. They can even write a beautifully structured sonnet about quantum physics.
Mm-hmm.
But then, if you ask this exact same genius to just walk from your living room down the hall and into the kitchen to get a glass of water.
They confidently try to walk straight through a solid brick wall.
Yes. They just smash right into it, back up, and then try to walk through it again.
It's so bizarre.
It's almost comical. But that weird juxtaposition of profound capability and just baffling incompetence, well, that's the exact paradox we are dealing with in artificial intelligence today.
It really is. I mean, it is the defining bottleneck of our current technological era. We are looking at systems that possess the sum total of human knowledge, yet they lack the basic common sense required to navigate a simple sequence of steps.
Right, without completely losing the plot.
Exactly. And look, we are assuming you, the listener, already understand the foundational concepts of large language models.
Yeah.
You know what a transformer is. You know what parameters are.
Yeah, we're not doing a 101 today.
No, today we are pushing past the basics and diving straight into the deep end of agentic AI systems.
And the mission for this deep dive is to unpack a groundbreaking piece of research that, frankly, claims to have solved that brick wall problem.
It's a massive claim.
It is. The paper proposes an architecture called the Modular Agentic Planner, or MAP. But what makes this research so compelling isn't just that they built a better AI, it's how they built it.
Right, because they didn't just throw more compute at the problem.
No, they didn't just scrape more data either. They essentially looked at the biological wiring of the human prefrontal cortex, realized that our brains are not monolithic, and then mathematically reconstructed that specialized system.
Using isolated instances of language models, which is exactly what we are going to dissect for you today.
So what are we covering exactly?
Well, by the time we wrap up, you are going to understand the precise mechanical anatomy of this MAP architecture. We will explore the rigorous, almost deceptive methodology the researchers use to test it.
Because proving an AI can actually reason is incredibly difficult.
Oh, it's famously difficult.
Yeah.
You have to prove it's not just regurgitating its training data. So we are going to look at the results, which, frankly, shatter the current industry baselines.
Completely shatter them.
And most importantly, we're going to translate all of this into practical, actionable insights for you. If you are building, designing, or even just utilizing autonomous AI systems, understanding this shift is going to be critical for your workflow.
It's the shift from prompt engineering to architectural engineering.
Exactly.
So let's start with the root of the problem. We see all these emergent capabilities in language models that surprise even the researchers who trained them.
Mm-hmm.
But the moment you introduce sequential decision-making, the moment a goal requires 5 or 6 dependent steps to achieve.
The illusion of intelligence just evaporates.
Right. Why is that? Why can an AI write complex Python code but fail at basic multi-step planning?
Well, it comes down to a fundamental lack of what cognitive scientists call cognitive maps.
Cognitive maps. Okay, unpack that.
For humans, and actually for most mammals, a cognitive map is a persistent internal relational structure that we hold in our working memory.
Like a mental blueprint.
Exactly. If you decide to go to the kitchen for that glass of water, you don't just start firing your leg muscles randomly. You access a mental geometry of your house.
Right. I know the hallway connects to the living room.
Yes. And you know the sink is next to the fridge, and crucially, you know that the wall is solid.
I'm projecting myself into the future, mapping out the route and predicting the physics of my environment before I take a single step.
Precisely. You mentally traverse that map, formulate a sequence of actions, and then you execute them. But a standard language model doesn't do that.
Because it doesn't have an internal geometry.
No, it generates text autoregressively. It looks at the sequence of words it has generated so far, and it just calculates the mathematical probability of the very next word.
It's just a purely feed-forward reactive process.
Right. It isn't looking 3 steps ahead. It's looking at the exact next tile on the board. And because it lacks that persistent internal map, it falls victim to very specific catastrophic failure modes when asked to plan.
Like hallucination. That's the famous one.
Yeah, but when we talk about planning, we aren't talking about hallucinating a fake historical date or a fake legal precedent.
No, we were talking about structural hallucination.
Exactly. If you place a standard LLM in a text-based navigation task and ask it to get from room A to room B, it might propose a path right through a wall.
It just hallucinates a non-existent door.
Simply because the sequence of tokens, move from room A to room B, looked statistically plausible based on the billions of words it read during training.
It doesn't actually know the wall is there. It's pretending the physics of the world match the probability of the text.
Right. And I assume that lack of a cognitive map also causes the system to just get stuck in a rut.
Oh, absolutely. I've seen models try to solve logic puzzles where they just repeat the same two actions over and over.
Infinite logic loops. That's the second major failure mode. The model moves from room A to room B, realizes it's not at the goal, so it predicts the most likely next step is
to move back to room A.
And then back to room B.
Obviously.
It lacks the self-awareness, the memory layer, to pause and say, wait a minute, I have been in this exact state before.
This specific action is not closing the distance to my objective.
Exactly.
I think the most helpful framework for understanding this limitation actually comes from Daniel Kahneman's book, Thinking Fast and Slow.
Oh, that's a great analogy.
Right. When a standard language model generates text autoregressively, just blurting out the next token, it is essentially operating as a purely System 1 brain.
Yes. In humans, System 1 is fast, intuitive, associative, and automatic.
It's how you catch a baseball thrown at your head, or how you instantly read a stop sign. You don't deliberate, you just react based on ingrained patterns.
And System 1 is incredibly powerful. I mean, the fact that we have built artificial neural networks that can replicate human System 1 intuition across almost all recorded text.
It's a miracle of modern computer science.
It really is. But System 1 cannot build a bridge. It cannot solve a complex algebraic equation. Complex sequential tasks require System 2.
System 2 is the deliberative mind. It's slow. It requires pausing, projecting into the future, evaluating different branching alternatives,
catching your own intuitive errors, and sometimes realizing that your initial gut reaction was completely wrong.
And our current models are brilliant System 1 thinkers, trapped in a paradigm where we're asking them to do System 2 work.
Exactly. And to be fair to the broader AI research community, they have known this for a while. We've seen various attempts to force these System 1 models to act like System 2.
Like chain of thought.
Right. If you are listening to this, you are almost certainly using chain of thought prompting in your daily workflow. That's where you append the phrase, think step by step, to your prompt.
Forcing the model to generate intermediate reasoning tokens before arriving at an answer.
Which definitely helps. It gives the model more compute time, essentially, by forcing it to output more tokens.
And then there's tree of thoughts, which is a bit more advanced. It allows a model to explore multiple reasoning paths.
Yeah, but even with those techniques, models still hallucinate in complex environments. They still fail.
So why wasn't tree of thoughts enough?
Because those frameworks still fundamentally rely on a monolithic system. Even in Tree of Thoughts, you are generally taking one massive language model and asking it to generate the ideas, evaluate the ideas, and choose the path.
It lacks strict functional factorization.
Think about it in human terms. You do not want the exact same part of your brain that is wildly brainstorming creative solutions to be the sole objective safety inspector of those solutions.
Right, because the generator is inherently biased toward its own generation. You need a separation of concerns.
You need a system where the dreamer is separated from the critic. Which brings us to the core innovation of this paper.
Okay, let's get into it.
To solve this inherently human bottleneck of complex planning, the researchers didn't invent a new type of mathematical transformer. They stopped trying to make the monolithic brain smarter.
And instead, they decided to slice it into specialized pieces. They built the Modular Agentic Planner.
Let's unpack the anatomy of this MAP architecture, because this factorization is the key to everything. Instead of taking one instance of GPT-4 and saying, here is the complex goal, figure it out, MAP is an ensemble. It is a highly structured recurrent loop of specialized LLM instances.
I like to visualize this as a construction crew. If you are building a skyscraper, you don't hire one hyper-intelligent person, hand them a hammer, and say, build it.
No, you'd hire an architect to draw the blueprint.
You hire a foreman to manage the schedule. You hire carpenters to swing the hammers.
Yeah.
And crucially, you hire a safety inspector.
Someone who doesn't build anything, but just walks around making sure the carpenters aren't violating building codes.
Exactly. And MAP has a very specific crew.
And for you listening, if you are actively designing autonomous agents, pay close attention to the mechanics of these modules. Each module in MAP is a separate instance of a language model.
Okay.
And they're controlled purely through highly specific zero-shot or few-shot prompts They are hyper-specialized. The first module is the task decomposer.
The architect.
Right. The task decomposer receives the massive high-level goal and the current state of the world. Its only job is to look at that gap and generate a manageable intermediate subgoal.
It doesn't try to solve the whole problem.
No, it just says, before we can build the roof, we need to pour the foundation.
Okay, so we have a subgoal. Now we need someone to actually do the work. Enter the actor module.
The brainstormer.
Right. The actor takes the current state of the world, looks at the subgoal provided by the task decomposer, and proposes potential actions. It says, okay, to pour the foundation, we could mix concrete, or we could order precast slabs.
But here is where the MAP architecture fundamentally diverges from standard models. The actor's proposed actions are not immediately executed.
They aren't sent to the environment.
Exactly. Instead, they are routed to the monitor module. And I would argue that the monitor is the single most important innovation in its entire paper.
The safety inspector.
Exactly.
Yeah.
The monitor is the absolute gatekeeper. Its sole isolated responsibility is to take the actor's proposed actions and rigorously check them against the hard constraints and physics of the environment.
Wait, let me stop you there because this is where a lot of people get confused.
Okay, go ahead.
If the monitor is just another instance of a language model, like the exact same underlying neural network as the actor,
Right.
why doesn't the monitor hallucinate? Why is it better at catching errors than the actor is at making them?
It's a brilliant question, and it comes down to the mechanics of prompt constraints. You do not ask the monitor to solve the puzzle. You give it a strictly binary task.
A yes or no question.
Exactly. Its prompt looks something like this. Here is rule A of the environment. Here is proposed action B. Does action B violate rule A? Answer only yes or no, and provide a one-sentence justification.
Oh, wow.
By narrowing the context window to a pure binary constraint check, you eliminate the autoregressive drift that causes hallucinations. The monitor isn't trying to be creative. It is executing a logical heuristic.
That makes total sense.
Yeah.
You constrain its operational freedom so tightly that it can't wander off the path.
Right. And if the monitor flags an action as invalid, say the actor proposed walking through that brick wall, it doesn't just silently delete the action.
It sends specific targeted feedback directly back to the actor.
Yes, it says your proposed action is invalid because it violates the constraint that walls are impassable. Try again.
It creates an internal dialogue of self-correction before any action is ever finalized.
Which is huge.
Okay, so the actor proposes actions, the monitor filters out the illegal ones. We now have a list of valid, physically possible actions. What happens next?
Now the system needs to know which of those valid actions is actually good. This is where the predictor module takes over.
Okay.
The predictor functions as the system's world model. It takes the current state, applies a validated action, and predicts exactly what the future state of the world will look like if that action is executed.
It simulates the immediate future.
It's the engine of imagination.
But imagining the future isn't enough, right? You have to judge it.
Right, so the predictor hands that imagined future state over to the evaluator module. The evaluator looks at that predicted timeline and scores it.
Usually, it's prompted to estimate how many steps are left to reach the ultimate goal from that new imagined state.
Exactly. It assigns a numerical value. Is this action pulling us closer to the finish line or pushing us further away?
And overseeing this entire operation is the orchestrator module.
The project manager is sitting at the top of the hierarchy.
It continuously monitors the current state against the active subgoal. It autonomously determines if the subgoal has been achieved.
And if it has, it taps the task decomposer and says, give us the next milestone.
And if the final ultimate goal is achieved, the orchestrator stops the loop, declares victory, and outputs the final verified sequence of actions.
It is a beautiful piece of engineering.
It really is. But I want to drill down into how the predictor and the evaluator actually coordinate, because earlier you mentioned the system explores different paths.
Right, the tree search.
Yeah. How does it handle multiple options without getting overwhelmed?
So when the actor brainstorms, it doesn't just propose one valid action, it might propose three. The predictor then imagines three separate future states, one for each action.
Okay.
The evaluator then scores all three of those futures.
So it's looking at branching timelines, like a chess grandmaster looking at the board.
Exactly. If I move my knight here, my opponent does this, and my board position is a +2. But if I move my bishop here, my opponent does that, and my position is a -1.
And the tree search can be recursive, right?
Yes. The system can look 2, 3, or 4 steps deep down each branch, evaluating the downstream consequences of a move before committing to the very first action in the present.
It rigorously calculates the optimal path based on those evaluator scores.
That's it.
Okay, I buy that this is highly structured, but honestly, how is this mechanically different from multi-agent debate?
Good question.
Because we've seen architectures where multiple LLMs are instantiated as different personas, and they argue with each other to find the right answer. Why is MAP better?
It's a vital distinction. In multi-agent debate, which is sometimes referred to as a society of mind approach, you do have multiple language models interacting, but they are essentially doing the same general task.
Like having 3 agents all prompted to solve a complex math problem.
And then they debate whose final answer is correct. It is a committee of generalists.
Everyone is trying to be the CEO of the problem.
Exactly. And because they're all trying to solve the whole problem, they are all susceptible to the exact same autoregressive hallucinations.
I see.
In MAP, the LLMs are highly factorized. The evaluator never, ever tries to propose an action. The monitor never tries to predict the future. They do one narrow thing perfectly.
That makes a lot of sense.
Furthermore, if you compare MAP to the Tree of Thoughts framework, MAP introduces control processes that simply do not exist in prior literature.
Right. Tree of Thoughts has the branching timelines, but it doesn't have the management structure.
Tree of Thoughts doesn't have a task decomposer to create hierarchical milestones. It doesn't have an orchestrator to autonomously manage the loop.
And most critically, it lacks the monitor.
Exactly. Tree of Thoughts combines the generation of ideas and the evaluation of ideas, but it does not have an isolated, dedicated safety inspector catching logical and physical errors before the evaluation phase.
The monitor is the absolute secret weapon of this architecture.
It really is.
Which is fascinating because this entire construction crew we just described, the specialized modules, the separate evaluator, the dedicated error monitor, it isn't just a clever computer science trick. It is a direct one-to-one translation of the biology inside your own head.
The researchers were explicitly inspired by cognitive neuroscience. They looked specifically at the human prefrontal cortex, the PFC, which is the seat of executive function, complex decision-making, and planning in mammals.
Because the prefrontal cortex isn't just one homogeneous blob of gray matter, it's heavily compartmentalized.
Right. Take the anterior cingulate cortex, or the ACC. In human neurobiology, the ACC is responsible for conflict monitoring.
Okay.
It is the specific region of your brain that lights up when you are about to make an error or when you encounter conflicting information. It suppresses inappropriate habitual responses.
Oh, wow. So the ACC is literally the biological equivalent of the MAP monitor module.
Exactly. It is the gatekeeper that suppresses the System 1 instinct to walk through the wall.
That's incredible.
And then you have the orbitofrontal cortex, the OFC. Decades of research show that the OFC plays a massive role in state prediction and state evaluation.
Okay, so it holds the cognitive map of your environment and estimates the expected reward or punishment of different situations.
Yes, so the OFC is our predictor and evaluator modules stitched together. It's the part of our brain running that tree search, imagining the future timelines and assigning an emotional or logical value to them.
Wow.
And finally, the anterior prefrontal cortex is heavily involved in high-level task decomposition, hierarchical planning, and managing coordination across multiple subtasks.
That's our task decomposer and orchestrator, the management tier.
Yes, they essentially built a synthetic prefrontal cortex out of black box language models.
But they didn't just lean on neuroscience, they also grounded this architecture deeply in classical reinforcement learning theory.
They did. And for anyone with an RL background listening to this, the parallels are going to jump right out at you.
Yeah.
The interaction between the actor module proposing moves and the evaluator module scoring them is a direct algorithmic translation of the actor-critic framework, which is arguably the most foundational concept in modern reinforcement learning.
Explain the actor-critic dynamic for those who might not be deep into RL.
Imagine a film director and a film critic working together. The director, the actor, creates a scene. The critic, the evaluator, watches the scene and gives it a score.
The director then uses that feedback to create a better scene next time.
Exactly. In RL, an agent learns to navigate an environment by constantly proposing actions and having a secondary neural network critique the value of those actions.
Got it.
Furthermore, the predictor module in AAP acts exactly like the world model in what we call model-based RL. A world model allows an agent to simulate the physics of the environment internally, so it can practice and fail in its own imagination, rather than having to physically act and fail in the real world.
But wait, here's where it gets really interesting to me. In traditional reinforcement learning, to get an agent to actually learn those actor-critic dynamics, you have to train it.
Right, extensively.
You have to put it in the simulation, let it interact with the environment millions of times, let it fail over and over, and slowly update its neural weights based on the rewards it accidentally discovers.
It's a massively computationally expensive training phase.
Exactly. And that is the pivotal difference here. MAP does not require that external million-episode training phase.
It requires zero weight updates.
Zero.
It relies entirely on the pre-existing general-purpose semantic knowledge already baked into the weights of the foundational language model. The modules act like highly trained RL components, not through gradient descent, but simply through precise architectural routing and a few zero-shot constraints in their prompts.
It's architectural intelligence. You take a generalist model that has read the entire internet, you force it to put on 5 different specialized tasks, you wire them together in a recurrent loop, and suddenly this text generator can navigate a complex spatial environment.
Which brings us perfectly to how the researchers actually proved this theory. Because talk is cheap in AI research.
Right. Having built this intricate, brain-inspired machine, they needed to put it into the testing arena.
And to their credit, they did not use standard easy benchmarks. They went out of their way to find environments that traditionally shatter the illusion of LLM intelligence.
Methodology is everything. If you test an AI on a logic puzzle that has been posted on Reddit 10,000 times, you aren't testing its ability to reason.
You are testing its ability to memorize its training data.
Exactly.
Yeah.
So they needed tasks that required true multi-step planning in completely novel, never-before-seen states.
The first testing ground they utilized is called CogEval, which focuses on natural language graph traversal. Imagine being placed in a maze of rooms, but you aren't given a visual map.
Okay.
You are only given a text description of the topology. Room 4 connects to room 7. Room 7 connects to room 2 and room 9, that sort of thing.
You have to build the cognitive map purely from language.
Exactly. And they ran 4 specific variations of this traversal task. The first was called value path. In this environment, you have to find the shortest path from a starting room to a specific destination. But it's a destination with a reward attached to it.
Right. I was looking through the source materials, and they visualize this brilliantly. Imagine you were in this maze, and there are 2 rewards available. In room 3, there is a small, pitiful pile of silver coins.
Right.
But in room 8, there is a massive, classic pirate treasure chest. Wood and iron binding, heavy lock, overflowing with bright gold coins. The AI has to find the absolute shortest path to the biggest reward, the treasure chest, while explicitly avoiding the room with the smaller reward.
It forces the model to hold a complex dual constraint in its working memory while simultaneously navigating a spatial map.
And standard autoregressive models completely fail at this because they get distracted by the first reward they encounter.
Yes. The second variation they ran was step path, which is just finding the shortest optimal path between any 2 arbitrary rooms. Then they turned up the difficulty with detour.
Oh, I love the detour test. They give the model the value path problem, It starts making a plan, and then suddenly, midstream, the researchers change the rules of the physics.
They inject a prompt saying the door from room 1 to room 11 is now permanently locked. But a new door just opened between room 4 and room 12.
It tests whether the system can dynamically update its internal cognitive map on the fly and recalculate a new optimal route without starting over.
And the last variation was reward revaluation, where the values suddenly flip. The big treasure chest is suddenly empty, and the small pile of coins is now worth millions. Can the model dynamically recalculate its final objective?
These are incredibly difficult tasks for standard language models because they require holding state.
But the researchers didn't stop at graph traversal. They brought in an absolute classic from the world of cognitive psychology, the Tower of Hanoi.
The Tower of Hanoi is the quintessential benchmark for multi-step, deep look-ahead planning. For those who might not have played it since childhood, you have 3 physical pegs and a stack of different size wooden discs on the first peg, arranged from largest on the bottom to smallest on top.
A perfect pairing.
Right. The goal is to move the entire stack of discs to the 3rd peg. But there are strict rules. You can only move 1 disc at a time, and you can never, under any circumstances, place a larger disc on top of a smaller disc.
It's a brilliant test of planning because it requires nonlinear progress. To solve the Tower of Hanoi, you frequently have to move a piece seemingly away from your final goal in order to free up a larger piece buried beneath it. You have to accept short-term divergence for long-term success.
But here is the massive methodological problem with the Tower of Hanoi. It is incredibly famous.
Oh, yeah.
It is mentioned millions of times across the internet. If you just ask GPT-4 to solve a 3-disk Tower of Hanoi, it will likely output the perfect solution.
But it isn't reasoning. It's just regurgitating the exact sequence of moves it memorized from a Wikipedia article during its pre-training phase.
It's contaminated data. So how did they test the reasoning without triggering the memory?
This is where the researchers made an absolutely brilliant methodological choice. They created a purely text-based isomorphic version of the puzzle.
Okay, isomorphic.
They stripped away all the semantic surface features. They deleted the words pegs, disks, tower, and Hanoi entirely from the prompt.
So what did they use instead to represent the game?
They used 3 abstract lists: List A, List B, and List C. Instead of physical wooden disks of varying sizes, they used pure integers, 0, 1, 2, and the rules were translated into strict mathematical inequalities.
Okay, walk me through exactly how this works, because this isomorphic translation is fascinating.
Let's say we have a 3-disk problem. In the starting state, List A contains the numbers 2, 1, 0. List B is empty. List C is empty.
Got it.
The goal is to get all the numbers into List C in descending order. So List C looks like 2, 1, 0.
Okay.
The rules are mathematically enforced. Rule 1, you can only move a number if it is at the very end of a list, represented at the top of the peg. Rule 2, you can only place that number into a new list if it is strictly smaller than the last number currently in that list.
Which perfectly mimics the rule of not putting a large disk on a small disk. Because if list B has a 1 in it, and you try to move the 2 from list A into list B, the monitor will flag it because 2 is not smaller than 1.
Exactly.
The physics of the wooden blocks are perfectly replaced by the mathematical inequalities of integers.
It is mathematically identical. The exact same logic tree applies. But because the prompt just looks like a weird array sorting task involving lists and numbers, the language model has no idea it is playing the Tower of Hanoi.
It cannot rely on pattern matching from its training data.
Right. It is forced to solve the problem from scratch, purely through active, in-the-moment reasoning. It completely eliminates data contamination.
Wow. Beyond these abstract clinical puzzles, they also used real-world adjacent tests, right?
Yes, they utilize PlanBench, which features highly complex logistics tasks. Imagine needing to move specific cargo containers between different cities using a limited fleet of planes and trucks.
Where the planes can only hold certain capacities and the trucks can only travel certain routes.
And within PlanBench, they used a notoriously deceptive domain called Mystery Blocks World.
Which, frankly, sounds like a terrible theme park.
It's a nightmare for language models. It is an environment where the names of all the entities and all the actions are completely randomized and obfuscated. So instead of pick up the red block and put it on the table, the prompt might say, perform action zeta on object glarg and associate it with blorb.
So you completely strip away the semantic common sense. The model can't rely on its intuition of what a table is or what picking up means. It has to rely purely on the underlying abstract logic of the instructions provided in the prompt.
Exactly. And finally, they tested it on StrategyQA. This benchmark tests multi-step reasoning in natural language with questions like, did Aristotle own a laptop?
I love these kinds of questions because to answer that, AI can't just do a database lookup. It has to decompose the question. Step 1, when did Aristotle live? Answer, ancient Greece around 300 BC. Step 2, when were laptops invented? Answer, the 1980s. Step 3, compare the dates. Conclusion, no, Aristotle did not own a laptop.
It requires sequential hierarchical logic.
So we have an absolute gauntlet of tests. Graph traversal with changing physics, isomorphic mathematical puzzles, obfuscated logistics, and multi-step historical logic.
And they pitted the MAP architecture against the absolute state-of-the-art baselines. GPT-4 zero-shot, GPT-4 in-context learning, standard chain of thought prompting, multi-agent debate, and tree of thoughts.
Okay, the tension is built. We have the architecture, we have the arena. How did MAP actually perform on the scoreboard?
The results completely shattered the baselines across the board.
I am looking at the data tables in the source material right now, and the numbers are honestly hard to believe. On the value path problem, where it has to navigate the text maze to find the big treasure chest of gold while avoiding the smaller trap reward, MAP solved 100% of the problems. A perfect score.
It outperformed every single baseline model.
And look at the Tower of Hanoi text translation, which we established is completely immune to training data memorization. On the 3-disk problems, MAP yielded a nearly 7x improvement over GPT-4's standard zero-shot performance.
And when they evaluated the system by letting it run 5 times and taking its best plan, MAP achieved a perfect score of 100%.
But the most stunning data point to me, the thing that actually made me stop reading and just stare at the wall for a minute, isn't the win rate, it's the error rate.
The zero hallucination phenomenon.
Yes. Wait, let me make sure I'm phrasing this correctly. Across all the complex graph traversal tasks, finding the treasure, dynamically adapting to the sudden detour, reevaluating the flipped rewards, the MAP architecture proposed exactly 0 invalid actions.
I'm Drew.
It never once tried to walk through a solid wall. It never once made a mathematically illegal move in the out-of-distribution Tower of Hanoi tasks.
Yeah.
0 structural hallucinations.
It's amazing.
Given how notoriously probabilistic and drifty these language models are, that shouldn't mathematically be possible.
It is a profound realization about the nature of these systems. A standard language model is inherently probabilistic. It guesses the next word based on a distribution curve. It is guaranteed to eventually make a mistake. But by embedding that probabilistic engine within this specific, highly constrained agentic architecture, by forcing every single proposal through the isolated binary logic check of the monitor module, they entirely suppressed the structural hallucination.
The system became perfectly rigidly constrained by the rules of its environment.
Exactly.
So, of course, the obvious question is, which part of this construction crew is actually doing the heavy lifting? Is it the branching tree search? Is it the task decomposer breaking things down? Or is it the monitor catching the lies?
To answer that scientifically, the researchers performed an ablation study. Ablation is a technique where you systematically remove or disable individual components of a complex system to see exactly what breaks.
Okay.
They took the 3-disk Tower of Hanoi problem and they started firing members of the MAP crew one by one.
Let's start with the safety inspector. What happened when they fired the monitor?
Absolute disaster. When they removed the monitor module and allowed the actors' proposals to go straight to the evaluator, there was a massive precipitous drop in the number of solved puzzles. But more importantly, the zero hallucination phenomenon vanished. There was a huge spike in invalid, illegal moves. It shot up to 31%.
Nearly a third of all its attempted moves were physically impossible just because the safety inspector wasn't there to catch them.
Exactly. It proved definitively that MEP success is not just about exploring multiple paths with a fancy tree search. Think about it. If you explore 3 different branching timelines, but your model is allowed to make illegal, hallucinatory moves along those timelines, the evaluator is going to score a physically impossible future as a good path, and the whole system fails.
The strict, modular, isolated oversight of the monitor is the linchpin that holds the reasoning together.
But the other modules matter too, right? It wasn't just the monitor.
Right.
Yes, every piece is load-bearing. When they ablated the tree search, essentially forcing the predictor and evaluator to only look one step ahead instead of branching, performance was severely impaired.
It proved that auto-regressive, one-step-at-a-time generation is simply insufficient for complex planning, no matter how smart the underlying model is. You have to be able to look ahead and simulate the downstream consequences of your actions.
And removing the task decomposer also crippled the system. You have to be able to break a massive, intimidating goal into bite-sized milestones.
What about the real-world NLP tasks? How did it do on StrategyQA, figuring out the historical timeline of Aristotle and laptops?
It was incredibly effective there as well. MAP scored 87.7% on StrategyQA.
Wait, I remember the baseline for that. Didn't actual human participants score 87.0% on that exact benchmark?
They did. The MAP architecture slightly outperformed the human average, and it decisively, cleanly beat traditional chain of thought prompting using the exact same underlying model.
Okay, so it's a massive, undeniable success. It mathematically mimics the biological prefrontal cortex. It uses a dedicated monitor to literally eliminate structural hallucination, and it beats human averages at complex logic deconstruction.
Oh, right.
And I have to push back here, and this brings us to the elephant in the room. Performance is only half the battle in the real world. We have to talk about efficiency, latency, generalization, and what I call the thinking slow tax.
It's the first question any engineer or developer is going to ask when they look at this paper. How much is this going to cost me to run?
Exactly. If a system is perfectly logical, but it takes 10 minutes and costs $5 in API fees just to decide to move a digital block from list A to list B, it is not practically useful for a production environment. System 2 deliberative processes are inherently computationally heavy.
The cost of deliberation is steep. In the MAP architecture, for every single microscopic step of a plan, you have the actor generating 3 proposals. You have the monitor running 3 separate binary checks. You have the predictor generating 3 separate future state paragraphs. You have the evaluator running 3 separate scoring prompts. And you have the orchestrator managing it all. That requires significantly more token generation and exponentially more API calls than just asking a standard model to think step by step.
So how did the researchers address this? Because if I'm building an autonomous agent to manage my calendar, I can't afford 100 API calls just to schedule a meeting. Did they just accept that true reasoning is inherently slow and expensive?
No, they recognized the bottleneck and they engineered an optimized version of the architecture. They realized that during a recursive tree search, the model is often generating predictions and evaluations for states that it might actually visit again later from a different branch.
There is a lot of redundant calculation.
Right. So they introduced a memory caching system.
So if the predictor has already imagined what the world looks like, if I move the 2 to list B, it saves that paragraph. If another branch of the tree asks for that same state, it just pulls it from the cache instead of prompting the LLM again.
Exactly. By caching and reusing the outputs of specific modules, particularly the predicted states and the heuristic scores from deeper search layers, they created what they call the efficient version of MAP.
And did caching the memory hurt the actual reasoning performance?
Not at all. The efficient version maintained the exact same win rate and the exact same zero hallucination rate, but it drastically cut down the number of redundant tokens and API calls. It proved that you can use standard computer science techniques to engineer your way out of some of the computational overhead of System 2 thinking.
But there is another, much more disruptive way to cut costs, right? You don't necessarily have to run this massive multi-agent loop on the biggest, most expensive proprietary model in the world.
This is, without a doubt, the most crucial finding for the developers listening to this deep dive. You do not need GPT-4 to run this architecture.
Wow.
The researchers wanted to see if the structure itself was the magic, or if it was just heavily relying on the raw power of the underlying LLM. So they swapped out GPT-4, and they dropped in a significantly smaller open-weight model, Meta's Llama 3 70B.
Okay, what happened?
While the Llama 3 version of MAP wasn't quite as powerful as the massive GPT-4 version of MP, it still performed incredibly well. In fact, Llama 3 70B running inside the highly structured MAP architecture actually outperformed the best GPT-4 baseline, which was GPT-4 using in-context learning on the complex Tower of Hanoi task.
Let me make sure I'm fully grasping the implication of this. A much smaller open source model, when correctly factorized into a monitor, a predictor, and an evaluator, beat a monolithic state-of-the-art GPT-4 model trying to solve the problem standardly.
Exactly. Architectural design beat raw parameter count. System structure beat model size.
That is democratizing AI right there. For you listening right now, this means you don't need to be entirely reliant on OpenAI or Anthropic's expensive API rates to build a high-functioning reasoning agent. You can pull a 70 billion parameter open-weight model onto your own local server, completely privately, structure it with this specific MAP architecture, and suddenly you are matching or exceeding GPT-4's native planning capabilities for the cost of electricity.
Furthermore, they tested MAP's ability to transfer these skills to novel situations, what we call out-of-distribution generalization. They took the MAP system, which had only ever been given examples of 3-disk Tower of Hanoi problems in its prompts.
Right.
It had never seen a 4-disk problem in its life. And they suddenly hit it with a complex 4-disk problem.
Which is exponentially more complex. A 3-disk problem takes a minimum of 7 steps. A 4-disk problem takes a minimum of 15 steps. The tree search branches explode.
Yes. And MAP successfully scaled to solve the 4-disk problems with a high win rate, without ever seeing a 4-disk example. The monolithic baseline models completely collapsed on this test. They solved close to 0%. MAP also showed superior transfer learning when moving from the normal Blocks World logistics task to that crazy, obfuscated mystery Blocks World domain.
It proves that MAP isn't just memorizing specific task rules. It is internalizing a robust, generalized, systemic method for problem solving.
Exactly.
Okay, this all sounds a little too much like magic. The architecture is brilliant, it beats humans, it works on smaller models. But as your resident devil's advocate, I have to ask, what goes wrong? No system is perfect. When MAP does fail, and we know it didn't get 100% on every single benchmark, how does it fail? Let's get into the failure modes, because understanding how it breaks is the most important part of practical implementation.
It's a vital question, and the authors were extremely transparent about this. They actually dug deep into the specific text log files of the runs where MAP failed the Tower of Hanoi task. They performed an autopsy to see exactly which member of the construction crew dropped the ball.
Let's hear the autopsy report. Who was at fault?
They identified 3 main failure modes. The first was incorrect decomposition. Sometimes the task decomposer, the architect setting the intermediate goals, will look at the board and set a sub-goal that was perfectly valid according to the rules, but didn't actually lie on the optimal path to the final solution. It took the whole team on a tangent.
It's a bad manager setting the wrong KPIs. The team executes perfectly, but they are building the wrong thing. What else?
The second and third failure modes were no progress and loops. This happened either when the actor completely failed to brainstorm a move that actually advanced the state, or, and this is more common, when the evaluator made a heuristic mistake.
A mistake in judging the value.
Right. The evaluator would occasionally look at a redundant state, mistakenly assign it a high numerical value, and lead the orchestrator to revisit a state it had already seen, creating a loop.
So the brainstormer ran out of good ideas, or the judge gave a high score to a fundamentally bad idea. But what about the rest of the crew? Did the monitor fail?
This is the most revealing part of the entire autopsy. Even when the system ultimately failed to solve the puzzle, the monitor, the predictor, and the orchestrator performed perfectly. The safety inspector never, ever let an illegal move through. The world model perfectly predicted the physics of the game every single time. The project manager perfectly recognized when a goal was or wasn't met.
The failures were isolated entirely to the creative generation of sub-goals, the brainstorming of actions, and the subjective valuation of value.
Exactly.
So, synthesizing all of this, what does this mean for you, the listener, who is actively building, coding, and designing autonomous AI agents today?
The biggest, most unavoidable takeaway is that the era of simple prompt engineering is over. Just trying to write the perfect paragraph-long system prompt for a single LLM is not enough to achieve reliable autonomy. We are entering the era of architectural engineering. If you want an agent that actually works without supervision, you cannot have one model to do everything. You must break your workflows down into specialized, constrained loops. You need a dedicated generation module, a dedicated evaluation module, and absolutely, unequivocally, a strict constraint monitoring module to catch the hallucinations before they hit your database.
It is the difference between hiring a brilliant but highly erratic, unpredictable polymath to build your house versus hiring a disciplined, highly structured construction firm. The firm will win every time because the structure absorbs the individual errors.
Exactly. And the authors even point toward the inevitable future of this research. They suggest that the next evolution isn't just zero-shot prompting of these modules using a general model. The future is jointly fine-tuning smaller, open-source models to serve exclusively as these specific modules.
Wow.
Imagine a highly optimized 8 billion parameter model that has been trained on nothing but being a perfect MAP monitor, or a perfect MAP evaluator.
Which leads us perfectly into the outro, and honestly, my favorite part of this deep dive. It is time for Novel Notions.
This is the segment where we pitch outlandish, highly speculative, but logically consistent new research ideas inspired by the mechanics of today's paper.
And before we begin, a very quick disclaimer for you listening. Please note this segment is entirely speculative and for entertainment purposes only. Do not base your medical, engineering, or investment decisions on novel notions. Okay, expert, you're up first. What wild idea did the MAP architecture spark for you?
I want to lean heavily into the neuroscience connection. The researchers explicitly mapped the MAP modules to the human prefrontal cortex. We know the monitor is the biological equivalent of the anterior cingulate cortex. We know the evaluator maps to the orbitofrontal cortex. My pitch is what I call the neuro-rehab agent interface.
Oh, I like the sound of that. A brain-computer interface. Where are we going with this?
What if we use an MAP-style architecture, not just to solve math puzzles or move cargo, but as an interactive, real-time cognitive prosthetic for patients with localized brain injuries?
Okay.
Think about it mechanically. If a patient suffers a traumatic brain injury or a stroke that specifically damages their orbitofrontal cortex, they lose the biological ability to accurately evaluate the future consequences of their actions. They become highly impulsive. They can't weigh risk.
Right. Their internal biological evaluator module is physically broken.
Exactly. So what if that patient wears an augmented reality device or even just a discrete earpiece paired with a camera on their glasses?
Yeah.
We deploy MAP architecture in the cloud, where the LLM evaluator module silently monitors the patient's visual environment and their potential real-world actions. It computes the value and the risk of those actions in real time.
Oh, wow.
And if the agent detects the patient is about to make a highly detrimental or impulsive choice due to their injury, say making a reckless financial decision or stepping into a dangerous situation, it provides gentle auditory feedback. Are you sure you want to buy that right now? Or perhaps we should wait and think about this. It acts as a cloud-based synthetic cortex, stepping in to perfectly perform the exact modular function the biological brain is missing.
That is absolutely unbelievable. You are using the factorized AI agent as a direct neurological bridge. It's not trying to be a general AI companion. It is acting as hyper-specific cognitive scaffolding for a specific biological deficit. I love that. I think we will actually see medical startups attempting that within the decade.
What about you? What is your novel notion?
I am hyper-focused on what we discussed regarding the computational cost of System 2 thinking and the author's suggestion to fine-tune smaller models. I call my pitch recursive module fine-tuning.
Walk me through the mechanics of it.
Right now, MAP is slow and expensive because it has to prompt a massive generalist model like GPT-4 over and over again just to get it to act like a simple binary monitor or a simple evaluator. But we know the MAP structure works perfectly on incredibly complex tasks. It generates perfect reasoning traces. So what if we use the slow, expensive, massive MAP architecture to generate its own replacement training data?
To train what exactly?
To train a swarm of edge compute micromodels. Here is the scenario. You take a massive multimodal GPT-4 MAP system and you let it run millions of complex logistics problems, graph traversals, and coding challenges. You let it run for months in a massive server farm. It is incredibly slow, it is insanely expensive, but it generates millions of perfect, verified, hallucination-free chains of logic. Then you look at the logs, you isolate the inputs and outputs of its perfectly performing monitor module. You extract only that specific data.
You now have a data set of millions of examples of perfect binary safety inspection.
Exactly. And you use that perfectly curated, flawlessly reasoned data set to fine-tune a tiny, lightning-fast 8 billion parameter model to do absolutely nothing but be a MIP monitor. It doesn't know how to write poetry. It only knows how to check constraints. You do the exact same thing for the evaluator, the decomposer, and the actor. You neurospecialize tiny models. At the end of the pipeline, you don't need the cloud anymore. You have a swarm of micromodels, each neurospecialized for one function, running natively and instantly at the edge on your smartphone. It is totally decentralized, insanely fast, practically free, but because of the architecture, it is perfectly coordinated to achieve GPT-4 level planning.
You are using the slow, deliberate System 2 deliberation in the cloud to permanently compile fast, intuitive System 1 reflexes for the edge device. That's not just a novel notion. That is a highly plausible trajectory for the next phase of agent development.
I genuinely think we're going to see that architecture become the standard within 2 years. But that wraps up our novel notions for today. Expert, leave us with one final provocative thought based on this MAP paper. Something for the listener to keep mulling over as they go about their day.
The paper proves that if we dramatically increase an AI's reasoning, simply by forcing it to talk to different constrained personas of itself in a highly structured loop, it raises a profound, almost philosophical question. Are we actually discovering a new, fundamental mathematical algorithm for artificial intelligence? Or are we just mathematically proving that the best, most reliable way to solve a really hard problem in the universe is simply to form a committee?
That is brilliant. Thank you all for joining us on this deep dive on Talk Tensors. Be sure to check the show notes for the direct link to the original research paper. And as you go back to building, coding, and living in this wild era of technology, keep questioning the underlying architecture of the AI you interact with every single day. Until next time.